Good evening, everyone. Today I will share about chemical energetics part 2. The content of today's lecture will be on entropy and free energy change, which relates to spontaneity of reactions. So these are the learning outcomes for the A-level syllabus. So in general, students need to understand entropy and how to discuss the effects of entropy on these factors, and also talk about standard Gibbs free energy, what is it, and whether a reaction or process will be spontaneous, looking at the sign of delta G, and understand its own limitations. Now, what is entropy? Entropy is a measure of disorder in the system. So if the system is more disordered, then entropy is larger. We can joke with our friend by saying, oh, instead of saying your room is very messy, we can say, oh, your room display a high entropy, which means his or her room is very messy. Now, entropy is a measure of different ways a system arranges itself. So a system with more different ways of arranging will have a higher entropy. So not only is a measure of disorder, it also means how many ways a system can arrange itself. So with more different ways, then entropy will be higher. So entropy change is a measure of the change in disorder in the system, and it only depends on the entropy of initial state and entropy of final state, which is its composition, volume, pressure, and temperature. So this is the very simple equation that relates the change in entropy. So if entropy change is positive, the final state is more disordered than initial state. If the entropy is negative, the final state is less disordered. So in general, there are 4 factors that affect the entropy of a chemical system. We shall look at each of them, starting with mixing of gas particles. Now, gas always mix completely to create a more disordered state. So upon mixing, each gas expands to occupy the whole container. So there will be an increase in entropy because there will be more ways for the molecules to arrange themselves in a larger volume. So if you mix 2 different gases together, okay, and when they mix, they will expand to occupy a larger container. That will mean an increase in entropy because there is more ways for the molecule to arrange themselves, more combinations. So increase volume, increase entropy. Or when you mix gas, it will be higher entropy. Now, how about liquid particles? For liquid particles, we are talking about liquids of similar polarities like benzene and hexane. So if we mix them together, it will form a solution in which the molecules are mixed. So the solution will have greater disorder than the liquids in the unmixed state. Because before they are mixed, they are not so disordered. But when you mix them, because they are of different liquid, so there will be more disordered. Next one, dissolution of ionic solid in water. So in the example of sodium chloride, when the delta S is greater than 0, so when you dissolve sodium chloride in water, it will involve the destruction of the crystal structure of solid sodium chloride and the hydration of sodium ions and chloride ions, which you learned in the previous chapter on what dissolution is about. So when you disrupt the crystal, it will increase disorder because previously the sodium and chloride ions are held in a rigid positions. Okay, but when the structure of the crystal is disrupted, it will be more disordered because now the ions are free to move. However, when hydration takes place, it will increase the order because it puts the water molecules into an orderly arrangement about the Na plus and Cl minus ions in forming a hydration sphere, like what is shown here. So it turns out that the overall dissolution process results in a net increase in randomness, and delta S is still greater than 0. In the case of calcium sulfate, where delta S is smaller than 0, calcium sulfate contains more highly charged ions, so there are more water molecules are ordered about the ions. So the dissolution process will result in a decrease in entropy. Yeah. So it really depends on what type of salts we're talking about. If the salt is of more highly charged, right, then there will be more water molecules to be ordered about the ions, okay, because of the charge. So because of that orderliness, right, the entropy decreases. So overall, you can actually have a negative delta S. Now, this is the Maxwell-Boltzmann distribution curve that shows the distribution of kinetic energy of a given sample of molecules at different temperature. So when temperature increases, there is a broadening of the energy distribution of the particles. So there are more possible energy states in which molecules can adopt at higher temperature. So with increase in temperature, of course, increase in entropy, quite straightforward. Because of increased possible energy state. So this is the key point. All right. Now, as for the entropy of solid, liquid versus gas, right, it's quite obvious that gas will have the highest entropy because there are more different ways of arranging the particles. From solid to liquid, when the solid melts, become a liquid, the order in the solid is destroyed. So the particles in the liquid are more disordered than the solid, which means an increase in entropy. For liquid to gas or solid to gas, right, it is also an increase in entropy, but the increase is much more compared to solid liquid because the gaseous state is very disordered. In fact, out of the three states, is the most disordered. So this change of phase is also accompanied by a large increase in volume. Next factor, the arrangement of molecules in a gas is the most disordered among the three states of matter because the molecules in gas are always in a constant random motion. So when the products of a reaction have more gas molecules, all right, than the reactants, the entropy increases like this. Because the products is gases, so entropy increases. And one example, you can just look at this example. So for these two processes, right, you may pause the video to predict whether it is positive or negative entropy change, and then justify. Okay. Let's go through. For the first one on the left is solid to liquid. So it is a change of state from solid to liquid. There's increased randomness and increased disorder. So the liquid state is of a higher state with greater disorder. So the liquid will have a higher entropy. So entropy change will be positive. But this one, right, is almost zero, very small, can be either positive or negative. There's really no change in the number of gas molecules because it's 2:2. So it's equal number of molecules between the reactants and product. So there is little change in the number of ways for the molecule to arrange themselves. Let's try this too. We can pause the video. Okay, let's try. For the one on the left, right, it will be greater than zero because liquid become gas. So gaseous particles have higher entropy because of greater disorder, and large amount of gaseous product will further increase entropy. So it's not just increase, but increase a lot more. How about this? On the right-hand side, this one will be negative entropy change because from gaseous, ions become solid. All right. This is like lattice energy, right? Yeah. So a decrease in entropy of the system because in this case, right, the solid have much lower entropy because particles in solid are significantly more ordered than a gas. Now let's talk about free energy now. What is free energy? So basically for A level, we just need to understand delta S and just a few equations. It's very basic knowledge of thermodynamics, very basic. So not to worry, just it, okay? We will not go any further. If you are interested, you can read up more, but that will be reading from the university text. What is standard Gibbs free energy? So Gibbs free change is given by delta G equal to H minus T delta S. So this is the formula that relates delta G to delta H and delta S and temperature. So the temperature has to be constant, okay? So standard Gibbs free, right, means it is at standard condition. So you can't use this at other conditions. So the standard condition will be pressure at 1 bar and a specific temperature 298 Kelvin, which is about 25 degrees Celsius, room temperature conditions lah. In general, we assume that delta H and delta S, please take note that when you have this sign here, it means standard. They do not vary significantly with temperature. So we have to make this assumption that they don't vary with the temperature. Okay, if not, this equation will not be valid. So you will use this equation very frequently in the questions. Now, a spontaneous reaction is one that can occur without any external system, meaning I just leave it there, the reaction will just occur without much interference, without much external interference. So, and normally for spontaneous reaction, it will be irreversible, meaning once it reacted to form the product, it's very difficult to be brought back to the original state using the same condition, unless you change the condition. But within the same condition, it's very difficult. It's like really irreversible. So a spontaneous reaction results in the system moving from a less stable to a more stable state. For example, ice melts spontaneously, but you do not have water forming by ice at room temperature. Of course, if you want to reverse the process, you have to bring down the temperature to allow freezing to occur. But at that condition, I'm talking about at that condition, it's impossible to make the reverse process occurring. So melting of ice at room temperature is spontaneous. So in this case, let's recap. Delta G less than 0 means negative. So if delta G less than 0, it means that, hey, the forward reaction is spontaneous. Thermodynamically feasible, it says to be exergonic. Exergonic means very, very feasible. But if you have positive value for delta G, means the forward reaction not spontaneous, it says to be endergonic. Okay. So what is some limitation in the use of delta G? Delta G indicate the thermodynamic feasibility, whether it can or cannot occur. But it doesn't tell us the kinetic feasibility, meaning it don't tell us whether it can result in the change within the given time we have. So it may occur, but because it take a long time, so it's like doesn't happen. For example, diamond to carbon, okay, or diamond to graphite. It is energetically possible, but not kinetically feasible, okay? So the kinetic feasibility will depend on the activation energy. So thermodynamic feasibility is not the same as kinetic feasibility. So that is the limitation. So if they ask you in exam A, what is the limitation of delta G? This is the answer. It tells us thermodynamic feasibility, whether a reaction can occur or not, but it doesn't give information about whether the reaction can proceed at observable rate. Meaning within the given time we have, can we observe? If it takes thousands of years, then forget it. We will not even live to that time. Okay. Now, these are some examples of calculation involving standard Gibbs free energy change, delta G. Not. So this is the equation. So for standard condition, it has to be at 1 bar and a specific temperature like 298 Kelvin, 25 degrees Celsius. And please take note of the units is kilojoule per mole. Okay, kilojoule per mole. But for delta S will be joule per mole per Kelvin. Okay, just take note of that. Okay, now, so we have this question. All right, calculate delta G for the following reaction. Okay, so these are the data given. So you can pause the video to try yourself before checking the answer and predict whether this reaction is spontaneous at 500 Kelvin. So these are the data given, delta H, delta S, you just have to substitute. And you also need to remember to, normally the delta S, right, they'll give in joule. But the problem is because the units are in kilojoule, right? So you need to convert joules to kilojoule first before multiplying by the temperature. And you get this. So more than 0 means not spontaneous, right? Remember Gibbs free say what? Less than 0 then spontaneous, right? So the next one, just do the same thing. And this will be a spontaneous reaction. Now, please check for consistency of units before you calculate. Now, what is the effect of temperature? Now, as we can see from the formula, temperature T is very important, and delta G really depend on it. And comparing the sign and magnitude of delta H and negative T times delta S, the sign of delta G can be determined by this 4 scenarios. Scenario 1, okay, let's say if the delta H is less than 0, delta S is more than 0, okay, that means at all temperature, you will expect the reaction to be spontaneous, okay? Now, but if you have a situation where your delta H is more than 0, delta S less than 0, then for sure, okay, it will be a small spontaneous reaction. So the delta S actually is very important. Or you have a situation where delta H is greater than 0, delta S also greater than 0. So only at very high temperature when this magnitude, right, will be higher than H, then it will be spontaneous. Because you need to make sure that the expression after the negative is greater in magnitude than the one before the negative sign. Same thing for here. So in situation 1, right, you have delta H less than 0, delta S greater than 0, will be spontaneous at all temperature. So for this scenario, right, delta G will always be less than 0. So it will always be spontaneous, thermodynamically feasible. Explanation is if you compare the sign of delta H and minus T delta S, delta H is less than 0 and delta S is more than 0, correct? So minus T delta S will be smaller than 0. So in that case, delta H and minus T delta S will be negative. These are some examples of such processes like decomposition, organic combustion, explosive. Okay, now let's look at this question. You have this situation where hydrogen peroxide decomposes to form water and oxygen. Very common reaction. Why delta H and delta S have the sign and comment on the feasibility? This is one common question. Just pause the video and think about the answer. So the solution would be delta S will be more than 0 means, okay, because you see, it's more than 0 because you can see that liquid there's a gas product here. So there's an increased number of gaseous molecule. So it's more disordered. I mean, the system is more disordered. Delta H less than 0 is because, right, water and oxygen are energetically more stable. Or you can say the bonds in water and oxygen are stronger. So more energy is released than more energy taken in. Delta H, you know how to obtain, right? It's the total energy taken to break the bonds in a reactant minus away total energy released when bonds are formed. So if delta H less than 0, it means that the bonds in these two products is definitely stronger than those in H2O2. Or you can say these two are more energetically more stable. So if you draw the energy profile diagram, these two will be at the below this one. So if that is the case, your feasibility will be if delta H less than 0, minus T delta S, both also minus 0. So this will be situation 1, correct? Situation 1. So it will be spontaneous at all temperature. That's it. Scenario 2. So in this case, you have a situation where your delta H is more than 0, delta S is less than 0. So in this case, right, it's a bad thing because it will not be spontaneous at all temperature. So if you compare the sign of delta H and minus delta S, delta H will be more than 0. If this is less than 0, then minus T delta S more than 0 at all T, right? So you add them together, it will be more than 0. Because delta H will be like so much larger, right? Yeah. So the reactions is not spontaneous, but doesn't mean it cannot occur because It can occur, but you need external assistance. It need to be driven continuously. So there's not external help to push the reaction to initiate, like photosynthesis or formation of ozone for oxygen. So there is some external help lah. You need to continuously run the reaction in order for the processes to occur. Okay, scenario 3 is where delta H and delta S are both positive. So the reactions are not spontaneous at low temperature, but spontaneous at high temperature. That means that, okay, delta G will be more than 0 at low temperature, where your T is less than your H, delta H divided by delta S. Yeah. So in that case, delta G will be less than 0. Okay, means very small T lah. Then it turns out that your delta G will be a positive value. In other words, if the temperature is high, that means T times delta S be greater than delta H, then your delta G will be less than 0. So comparing the sign of delta H and minus T delta S, so delta H more than 0, then if delta S is more than 0, then minus T delta S will be smaller than 0 because minus ma. So at low T, the sign of delta G is determined by the sign of delta H. Okay, so whatever sign delta H is assigned, then delta G will be accordingly. So the positive delta H term outweigh the negative minus T delta S. So delta G will be more than 0. At high T, right, the sign of T will be determined by minus T delta S. So the negative will outweigh the positive. So delta G will be less than 0, will be thermodynamically feasible. Now, example 4, you have this process. You need to explain why delta H and delta S have the sign and command. You can pause the video first. Okay, for this case, right, delta S more than 0 because you can see that there is a breaking of the lattice structure into ions, and this is definitely more disordered. So your delta S will be greater. All right. Is that greater than the orderly of the water molecules around the ions? Because the charge is not so high also. So you can expect that, oh, delta S is more than 0 because the charge is not very high. Then delta H more than 0, if you recall the previous topic, delta enthalpy change in solution equals to enthalpy change in hydration minus lattice energy, right? If you recall this, right? If this is positive, it means the lattice energy is more exothermic than the sum of the delta H, the enthalpy change of hydration. Yeah. So more exothermic, meaning this value will be, yeah, positive. Because lattice minus, so minus will become positive. Yeah. So at low temperature, the delta G will be positive because the positive delta H outweigh the negative minus T delta S. At higher temperature, the negative T delta S outweigh delta G, so delta G become negative. So the reaction is not spontaneous at low temperature where delta G is positive, but spontaneous high temperature where delta G is negative. Okay? Okay, situation 4 is both of these is less than 0. So directions will be spontaneous at low temperature, but not spontaneous at high temperature. So you need to roughly remember the processes. Okay? Yeah. All right. So at low temperature, delta G is less than 0, and high temperature is more than 0. So examples like condensation, freezing, addition, and combinations, reactions, electrochemical cells, and precipitation. So, okay, I think I will not go on to this. You can just read yourself. So example 5, you can study this question and try to do. Okay, now, so in this case, right, comment on the feasibility. So at low temperature, delta G will be less than 0 in this situation. Okay, both less than 0. So negative delta H outweigh the positive minus T delta S. At higher temperature, it will be the other way around. So the reaction is spontaneous at low temperature if the negative outweighs the positive, but not spontaneous at high temperature. So this is a summary. And let's try this question. I think I won't go through the question. Okay, we will just stop here on the summary. So this will be a summary of today's lesson. I hope you enjoy the lesson. I hope this is helpful to you lah. Okay. Thank you.